So today we have quite interesting topic related to the search, linear search, and we decided that it would be great to handle this lecture offline. So today Valentina will support me with that, and will handle this lecture. So Valentina, floor is yours. Recording started, and I propose to start with the lecture.
Thank you, Roman. So, hey guys, today we are having a lecture, and our topic is linear search and binary search. So, who already knows about these searches? Okay, that's okay. So, why do we need search? How do you think? Yeah, so when you have some data set and you want to find an item. So basically, you just were passing an assignment about linked lists, and when you were searching for a node, you were going through like all elements, and you were like also searching. So search is really important stuff because you search all the time. For example, you search for a pizza in the Domino's application and so on by the name and stuff. You search in Google and so on. So basically, search is a very, very common problem, and we will today cover two types of search: linear search and binary search. The key difference between them is that linear search is slower, and binary search is more optimized algorithm. Let's start from the linear search. So basically, you have an array of elements, an unsorted array, just a random array. And we go iterate through every element and look if this element equals to what we are searching for. And if not, we go to the next element and we return the index. Basically, that's all. We just traverse an array. Is it clear? Great, because it's pretty easy, I think. So, as I told, traverse the array, compare elements. If found, we return index. If not found, we return -1, for example. What is the time complexity of this algorithm?
N.
O(n), yes, O(n). So n is the number of elements in the array, and the worst case scenario is that element what we're searching is the last one. So O(n). Yeah? Yep. Okay. So like really simple realization, we just iterate through an array, and that's all. Take a look and we can move next. Recursive method. So we can also create a recursive method of linear search, and you can check out the realization. So if the array is empty, then we found nothing. Then we just go from the end of the array and look if the last element is equal to key. If equal, returns the index. Here is the index, and if not equal, we call this method again, and we pass the same array, but we pass the size -1, so we skip the last element, and we start from the element before the last element. Okay, so like we had, I don't know, 5 elements. We started from this, then we pass size -1, then we don't look at this anymore, and we start with this. What do you think? Everything's okay? Yeah, so I don't know, the plus of this method is that it looks, I don't know, it doesn't look elegant for me, by the way, but you should know that we can do it through the recursion, the complexity is the same, we can do that, but we should be really careful because at one moment size -1 will return 0 because there will be no elements left. So that's why we have this check. If size equals null, return -1. Okay, so basically, this is not really optimized algorithm because if the number of elements grows, then the complexity grows proportionally. So we can have 10, 100, 1 million elements. So if there is 1 million elements, you can imagine how hard it is. So this is definitely a minus, but from the advantages, it is a really easy implementation. So yeah, but we have binary search. Binary search is optimized algorithm, and you can look at the screen and look how it works. So basically, it's like, imagine that you are playing a game with your friend and you are trying to guess a number from, I don't know, 0 to 100. And you ask your friend, like, is it 50? And your friend says, no, it's less than 50. And you, is it 25? And your friend says, it's more than 25. So you're like continuously dividing your data by 2. And that's how you search for the number. But it works only with the sorted arrays. So like in my example, from 0 to 100, you just continuously divide by 2, and you go either at the left half or to the right half. So look at the GIF. Like how we're looking for the element. And then it starts again. So we search for the middle position. Here, we're searching for the 5. We are looking that 5 is less than 7. Then we go to the left half. We discard right half, and we look here. Now we're also look for the middle element. Now our middle element with index 1. Here it is. And we look, 5 is more than 3. Then we discard left half, and we have only 2 elements left. And we divide by 2 again. And we round this number. And now here's our element, and we again compare these numbers, and we discard the left half, and we do it until only 1 element left. So is it clear, or should I draw on the... It's clear for everyone? Everyone? Okay. So basically, it is really quick. So why we do it? Because we can achieve a complexity of log n. Why log n? Look here. So when we use linear search, the more elements, the more iterations proportionally. But when we use binary search, as we continuously divide by 2, then we have the logarithm with logarithm for like 2. And for example, if we have 8 elements, then we divide 3 times, because 2 power 3 equals 8. So if we have 8 elements and we keep dividing our array by 2, then we need only 3 iterations. So if it would be like linear search, we would have 8 iterations, but with binary search, we have only 3. So it's like really optimized search, but it works only with sorted data. So, but you can like sort your data first and save it in your database in the sorted manner, and then your search will be really effective. So why do we need this? Because, for example, imagine you're buying a ticket on this website for a plane. I'm sorry, guys. Not to mention that you're doing that, and if your search will be really would take a long time, then you would go to the concurrence of this company. So your search should be really fast for the user, because when we are talking about real world application, every second matters. So if your app runs for a couple of seconds, it is bad. So you need to fight for every second. That's why we use optimized algorithms. So let's see the code. So we have binary search method. We have an array, and we have the element which we are searching for. The left index is 0, it's the first element, and the right index is length -1, the last element. And while left is less or equals right, while we have elements to traverse this array, we will search for the middle element like this. And then, as we discussed, we check if this element equals the search, the middle. That's great. We found our element by 1 iteration. If not, then we either go to the right half, so left element will equal middle +1, This is our new index. So we discard the left part and we go to the right part. Or we discard the right part and go to the left. So I will draw just in case. So we have an array of elements, and we are searching for this. For this. We're searching for this. So first, what we do, we find the middle element. This is this one, and we check. Is it higher than the element we're searching for? For example, this is 3, and this is 7, and we check. If it is higher, then we just discard that part. And we continue look in this part. And we also look for the middle. It should be this one. And we found this element basically. It's clear? Yeah? Okay. And I also will show you the recursive version of this method. It looks beautiful, I think, but you also should be careful to not get the Stack Overflow and not to go to the infinite loop. So the same stuff. We are looking for the middle index. We compare the elements, and if middle element is less than search, then we should go to the right part. And as you can see, we are passing the... Oh, oh no, please. Yeah, so as you can see, we will just, we are passing the first index and the last index. So when we call this method for the first time, we are passing here 0, here 0. Oh no. And size -1. But if we discard the left part here, so we will call this method with my new indexes, and the first element will be middle +1, and the last will be size -1. And the same here. If we discard the left part, then the first index is still 0, but the last index is middle -1, because we don't need this anymore, the right part. So, is it clear?
What is mean and what is low and what is high?
Yeah, so these are our indexes between which we conduct our search. When we call this method for the first time, we need to pass the whole array. That's why here in the low we pass 0, and at high we pass size -1. Then we are finding middle element, and we look if middle element is less than search. This means that search is in the right half. So for the next iteration, we call the same method, but we start not from the middle +1. This is like this element in our case, and we start from this element, middle +1, to the last element, size -1. And we call the same method, but for this part. Yeah? Okay, basically it is all for today. I don't think that it is like a very hard topic. So I am proposing to you just to write by yourself all these methods. Linear, recursive, binary, recursive.